Okay, so question 5a says we should explain why I u1 equal to 1 2, u2 equal to 0 3, and u3 equal to u3 equal to 2 7 are not basis for, let me see if I can finish this. Are not basis for R2. Why are these three vectors not basis for R2? Okay. Okay, so of course, you know, by definition, let me also try to write the second part. The second part is also almost the same. So there we have u1. Let me use this. So we have u1 equal to minus 1 3 2, and then u2 equal to u2 equal to 6 1 1. Okay, are also not a basis for R3. Why they are also not basis for R3? Okay, so let's see. Okay, so what do you explain as the reason why they are not basis? First of all, vectors are a set of vectors will form basis for a particular vector space. Number one, if they are linearly dependent, and number two, if they span the vector space. Okay, so however, in this question is just a very simple trick they are trying to work on you, because the vector space already has its basis obvious here. So this is R2, and so you expected to know that the basis for, it already has its dimension, not basis. This is the dimension showing you here that this is a vector space of dimension 2. And then this one is showing you that this is a vector space of dimension 3. Okay, so, and you remember that the dimension is the number of vectors in the basis of a particular vector space. Okay, so that is to say that these three vectors cannot be in the basis of the vector space R2. Okay, so because the vector space R2 has a dimension of 2, and so the basis should only contain 2 vectors and not 3. All right, so you can just state it that basis for R2 should contain only two linearly independent vectors. Remember I said it here. 2 linearly independent vectors that span R2. 2 linearly independent vectors that span R2. Not 3. Okay, so not 3, but that the reason you're saying not 3 is to let them know that this one has 3. that this one has 3 vectors, and so you are not going to have it as a basis. And the same thing applies to number 2. The basis for R3 should also contain only 3 vectors. Should also contain 3 vectors. Let me put that one that way. Should contain 3 linearly independent vectors that span R3. Okay, so that's exactly how this should be. Okay, that span R3. Okay, all right. So, and you can also say not 2. Okay, so that's the idea for your for the basis of a particular vector space. And that's why they took time to provide the vector space for us, so that you will know already what the dimension is. Okay, so, and that is that. Okay, so we go to the next one, which is bi. We are told to state 2 vectors that we know which are linearly dependent vectors. This one is a very simple question. Linearly dependent vectors. I have taken time to mention linearly dependent vectors many times here. So 2 examples. Okay, that's what they are looking for in this particular question. So all you need to do is just put up any vector as your u. For instance, maybe something like 1, 0, 2, and then put up a multiple of it. Just put up any multiple of 1, 0, 2. Say 2, 0, 4. This is a multiple. I multiplied by 2 to get this. Another person can put up anything, multiply this one by minus, maybe something like minus 1, 0, minus 2. Something like say 5, 0, 10. I multiplied by 5. Or you can multiply by a negative number, minus 3, 0, 6, minus 6, and so on. So just put up any vector, and then you will just take a multiple of it. So that will give you 2 vectors that are linearly dependent. All right, so, and then we go over to the second part. There they said, under what condition will a set with 1 vector be linearly dependent? Okay, so what will make a set of only 1 vector be linearly dependent? Okay, so what does it mean for a vector to be linearly dependent? All right, okay, so here you can see that if you have a 0 vector, if we have a 0 vector, for instance, you can see that it can on its own be linearly dependent. Okay, so okay, yeah, so it can be linearly dependent on its own, thus being a single vector. Okay, now because the value will just be, of course, a 0 vector will just have 0 entries on every of the components. So you can try that. Okay, so as an answer, so it has to be a 0 vector to be a single vector that will be linearly dependent. Okay, now let's go to question C. So for question C, we are told to let S be the vector 1, be equal to 1 plus t. Okay, let me remove that bracket. They didn't put that. 1 plus t, and then 1 plus t squared, and then t plus t squared. Okay, so they said let this be a basis for the vector space. Let it be a basis for the vector space. And what's the vector space now? For the vector space P2. And what is P2? P2 is actually the vector space of polynomials of degree 2. And they actually mentioned it here. Of polynomials degree 2. Okay. Polynomials of degree 2. That's P2. Okay, and you can see it here. The highest degree there is 2. Okay, then it says find the coordinate. Find the coordinate vector. Find the coordinate vector PT equal to the coordinate vector of this polynomial P of t equal to 6. There we have 6 plus 3t, then minus t squared. Okay, relative to s. You know, whenever we are looking for coordinates, the coordinate vector of a given vector, so it is always relative to a particular basis. All right, so what do we do here? To get the coordinate vector of this particular P vector P relative to that vector space that we are given, remember we have done examples like that using normal vectors and not polynomial vectors. So here what you're going to, or what we expected to do here, is simply to try to express this vector P as a linear combination of the dimension, of the basis that you're given. Okay, so what invariably will you do? So remember that these are all vectors of their own, and they all make up the basis. So that means this basis consists of those 3 vectors. So what you expected to do here now is that we are to find, we are to find some C. Of course, they even wrote it here. So we seek for some C, C1, C2, C3, so that to find C1, C2, C3, so that the time you use those C1 to multiply the first element in the basis plus C2 multiplying the second element in the basis, and then plus C3 multiplying the third element of that basis, everything should be equal to your P of t, which is 6 plus 3t minus t squared. Okay, so what that means is that you are actually looking for the coefficients that you just inserted here, the values of those constants. Once you are able to get the values of those constants, put them as a column matrix that will give you the coordinate vector of this particular vector P here. So what we are looking for here is the value of C1, C2, C3. Okay, so, and all you need to do is to open the bracket and then compare coefficients of constants, and then coefficients of t, coefficients of t squared, and that will be all. So you will solve. Okay, so what do we do? Open this bracket. So we will have C1. Okay, I'm going to be bringing together all constants. So C1 plus C2 are going to be constants. Then plus C1 times T. Then another one with T is, maybe I should use a different color for the ones that carry T. Okay, so C1 C1T, then plus C3T. Okay, and then next the ones that carry squared. We are done with this. We come here, so this is C2 squared. Remember that I've picked this first one, which is this, and then you now pick this last one, which will be C3 t squared. Everything is equal to 6 plus 3t minus t squared. Okay, so what will happen now is to now compare coefficients. Of course, here you can factorize your t. If you factorize t here, you have c1 plus c3 all in bracket t. So let's write it that way. So I was using this c1 plus c3 all in bracket t, and we'll do the same thing here. Bring out t squared, so you have c2 plus c3. Okay, so c2 plus c3 all in bracket t squared, c2 plus c3 then bracket t squared. Okay, so if we now compare coefficients now, or both sides of the equation, then c1 plus c2, which are the constants, should be equal to 6, equation 1. Then also look at it here, c1 plus c3 should be equal to the coefficient of t on the right side, which is 3, equation 2. And then also c2 plus c3 should be equal to the coefficient of t squared, which is minus 1. Call this one equation 3. Okay, so we now try to solve these 3 equations to get our c1, c2, c3, and that's all. So what do you do here? You can easily substitute one of the equations into the other two by making one c the subject. So if I do that in equation 3, so from equation 3, I'm going to have that c2, is that okay? Let's see. So I'm going to have that c2 is equal to minus c1 minus c3. Okay, so if I substitute that here into c1, I am going to get into equation 1, I'm going to get only c1 and c3, and that will be similar to equation 2. Then I can solve the two of them. So put in equation 1, you will get, if you put it in equation 1, you are going to have c1 plus our c2 now is now equal to minus 1 minus c3, okay, and that's equal to 6. So we simplify that, and in doing that you have c1 minus 1 minus c3 equal to 6. So let minus 1 come over, we'll get c1 minus c3 equal to minus 1 coming here will become plus 1, which will give us 7. And so we have gotten that equation now as that. So if we solve it together with equation 2 in a simultaneous approach using probably elimination method, if you add this here, c3 will eliminate. So we are going to have 2c1, and then this and this will go away. So on the right you have 10. Therefore our c1 is equal to 5. So we have gotten c1 as 5. That means we can easily get our c3. Let me do that here. So to get our c3, just substitute into any of these two equations. If I substitute into equation 2, my c1 plus c3 equal to 3. So what did I get as c1? 5 plus c3 equal to 3. So that means that c3 alone is equal to minus 2. Sorry, that will be 3 minus 5, which is minus 2. And then my I've gotten c3 and c1. Then from here I can get my c2. I already have a relationship between c2 and c3. So my c2 will be equal to minus 1 minus 2. And therefore c2 is equal to 1. So finally, you can bring all together. c1 is 5, c2 is 1, and c3 is equal to where is it, C3 is minus 2. Okay, and so what that means is that the coordinate vector of matrix P that you are looking for under basis S is going to be equal to, put all those your values in column vector starting from C1 and then C2 and then C3, and this is your solution. So that is the value for the coordinate, that's for question C. Okay, so we move over to question D of number 5 of module 4, which I think is the last question. Okay, so there is E. So question D says, let A be a 3 by 4 matrix. Okay, it says if the null space of A is a subspace, of Rk, that's R to the power of k, meaning R with basis k, or sorry, with dimension k, then what is the value of k? That's what they asked in question 4. What is k? All right, so what is that trying to say? That you have a matrix of dimension 3 by 4, and then it says if the null let A be a 3 by 4 matrix if the null space of A is a subspace of Rk. So what is that? Okay, so what that means is that, you recall there was a time we worked on a particular matrix. So let me use this as an example. Let's take it that you have a matrix. Remember that when you talk about dimension, before I get there, dimension is always row versus column. Okay, sorry, row versus column. All right, so that means this particular matrix has a 3 by 4 that is 3 is the row and then 4 is the column. Okay, so it's something of this nature. Let's say A, B, C, and then D, E, F, and then G, H, I, and then you have maybe 0, 0 here. So because it's talking about a null space, so that means you have 4 columns and then 3 rows. And then you know that it is the column vectors that usually determine the basis of a particular vector space. And then, of course, the number of vectors on it will now give you the dimension. So since this particular matrix is going to contain about 4 columns, so it implies that the dimension of that vector space will be R4, and so our k is equal to 4. All right, and that is for number 5D. That's all. That's not a big deal. It's just a question that demands that you understand the concept of dimension and basis. All right, so then E says let A be equal to, so you have 2 minus 2, 3. Then here you have 4 minus 5, 7. Then here we have minus 2, 7 minus 8. Then you have 1, 3, 6. Okay, so it says which of these vectors, and then they gave us about 2 vectors. Let me try to write them here. So they said u equal to 3 minus 2 minus 1 0, and then v equal to 3, then we have minus 1 and we have 3. They then said is in the null space, is in the null space of A. Okay, so it says which of them is in the null space of A. All right, so whenever you're talking about a null space, so it's just a vector. The null space of A now is a vector that will be in the null space of A is a vector that a null space is that you have A times a vector equal to 0. So all the vectors that will multiply A and then the result will be 0 are vectors that are in the null space of A. Okay, so vectors, if it is in abstract algebra, we refer to that as I've forgotten that term now. Remember it. Okay, so and then so what this is looking for are all x values that will satisfy this particular equation. Okay, so all you need to do is pick these 2 vectors, multiply with this matrix, and see which one will give you 0. So that's what we want. Okay, so we want x that will satisfy, let me put it that way. We want vector x that will satisfy Ax equal to 0. So I'm just going to substitute my x as u and as v. And of course you can see that I wouldn't know if this is a mistake from them or from the producer of the material. V has only 3 entries, and if it has only 3 entries, it cannot even multiply A, because the only way V can multiply A or any other vector can multiply A is that the number of columns should be the number of rows here, so that when you multiply matrices, you pick it this way and multiply this way. So this element must multiply, this one will multiply, this one will multiply, and then this one will multiply. But this has only 3. So if the first 3 multiplies, there is nothing here to multiply this one. I don't know if you get what I'm saying. Okay, so that means we are only going to try u. So v is already out of the case. So let's try u and be sure before we conclude. So if u does not satisfy the equation, so what it means that none of them is in the null space of our A. So we have -2, -1, and then 0. Okay, so let's do this multiplication. Let me come up. Okay, so to do that multiplication, we are going to get another matrix. So the whole of this will multiply. 1 times 3 is 6. 4 times this is -8. -2 times this is +2. And 1 times 0 is 0. Okay, we go over here. -2 times 3 is -6. -5 times this is +10. 7 times -1 is -7. And 3 times yeah, and 3 times 0 is 0. Meanwhile, let's be sure this times this is minus 6, this times this is 10. Okay, it's correct. And finally 3 times 3 is 9. 7 times you can already see that this one has failed it, so it's not in the null space. But let's finish. 7 times minus 2 is minus 14, and then minus 3 times this is 3, and then this times 0 is 0. So you can see that this is equal to, the first one gave 0 quite alright. The second one did not give 0. The second one gave minus 3, and then the last one also did not give 0. There we have this plus this is 12 minus this is minus 2. Okay, so there we produce the 0 minus 3 minus 2, which is not equal to 0 vector. And so this implies that neither u nor v is in the null space, of A. Okay, and that is the solution for that question E. Alright, and yet there is another question. I thought that E was the last, but I'm seeing F now. Okay, so let's look at question F. So there we are told to I find the dimension of a subspace V of all vectors in R3 whose second and third entries are equal. And then it now says find also the basis of V. Okay, and there is a hint there. V is of the form blah 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 that. Number 2, the set this is a basis of V. Present another set of bases. Okay, and then all of that. So, and I'm going to leave that F for you all as exercises, so that will form a difference in whatever you're doing. Okay, so I will leave that. Let me write it out. Okay, it says find the dimension of the subspace. The subspace V of all vectors in R3. Okay, whose second and third entries are equal. Okay, all right. So, and then they said find also find also the basis of V. Okay, so you are looking for the dimension and basis of V. Okay, basis for V, sorry. All right, so that's the last question. Okay, there is actually a thought there. Show that the members. Okay, that's just under the hint, and there are hints that they gave you there. So just take time to do that and then see what you will get. And this is the end of module 3. This is the end of module 3, and so we are going to continue to module 4 if we are able to do that. Should I, or we should go over to, to module 5. Sorry, or we should close and then open another one for module 5. Okay, let's see. Okay. Okay. Okay, module 4 stopped at page 34, and it's just a little. So let's see if we can finish module 4 in this particular video. Okay, so let's open, let's go to another page for module 4 now. Okay, so we have module 4. Let me reduce this even. Should I leave it that way? Okay, let's see. Okay, so here we go over to module 4. I'm trying to see how long this has been so as to know what we are doing. Okay, 48. Okay, let's see module 4. All right, so module 4 says that we should module 4 is going to be concentrating on still on systems of equations, and then maybe matrices. Okay, so okay, so let's see. All right, we go. So let me read the introduction. It says, for us to enjoy this module, we must be familiar with the following concepts: the four-dimensional subspace, null space of null space of A and A transpose and its dimension, column space and its dimension, row space and its dimension, and how they connected, rank of a matrix, and so on and so forth. Okay. So we begin with the first question. All right, it says, given that you have matrix, given that U and V are subspaces of R4 with U equal to that and V equal to that, it says find the basis and the dimension of U, V, and U intersection V. And they did that by allowing us follow some steps of filling spaces. Okay, so let me try to write the question. So given that U and V are subspaces of R4 with, so that's another way, where U is given as the set of x1, x2, x3, x4, such that 7x2 plus x3 plus x4 is equal to 0, and then V is the set of x1 such that x1 plus x2 is equal to 0, and x2 is equal to 5x4. Okay, so it says we should find the basis, or find a basis and the dimension okay, we should find at least one basis and then the dimension of the following. So the first there is U, then V, then U intersection V, or union intersection. Okay, intersection V. Okay, So that's what we are to do. Okay, so what is that going to do for us? Let's see. Okay, so they started by giving us solution and then some steps to follow in doing that. Okay, so they said fill in the gaps for us. Okay, so the first thing is, do you realize that u can be written as ax equal to 0? Okay, of course, you should be aware that you can actually write this u in terms of matrix and what do you call it? A matrix multiplying a vector. Okay, and then the right side will be 0. So look at it here. Our u is 7x2 plus x3 plus x4 is equal to 0. Okay, let me put it this way. This is equal to 0. So of course this is the same thing as okay, let me put it here. This is the same thing as having your, of course you always can bring out the coefficients here to form a matrix 7 1, and then it will not start from 7, it will start from x1, and x1 is missing here. That means 0. So you have 0 7 1 and 4. The coefficient of x4 is also 1, and so you close the bracket, and that is going to multiply your x1 x2 x3 x4. Of course, if this multiplication happens, you will still get back this, and that is equal to our 0 0 0 0. Okay, that's just 1 0. It should be 1 0 because it's only one equation that we have there. So it's only equal to 0. We can just put it that way. And so if that happens, therefore and then they now said from there, okay, so we should find a. So I've already given you the a's. This is remember they said we should express it as ax equal to 0. So that means our a is the matrix, x is all these values of x, and then you have your 0. So you have your a, therefore, as let me put it here, therefore our a is equal to the matrix 0 or the vector 0 7 1 1, any one. Okay, and then it says again, okay, then it says we should find, what about x? So our x, okay, they even asked us to find x. Okay, I thought it was only a. Okay, our x is just this one, x1 to x2 to x4. So you can put it this way, x1 blah 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 up to x4. So that's our x. Okay, or you can even put it in full to avoid writing what you do not know. So this is x2 x3 and then x4. Okay, so that's our x. I chose to put it in a row. You can also put it in column if you want. That's the way I left it here. All right, so what then is the next question or the next step? Remember, we are looking for the dimension and basis of u, v, and u intersection v. So but we are following the steps they are giving to us. So they said again, the solution set of u is a subspace of Rk. Okay, yeah, because okay, of Rk, where k is equal to. So of course here we are already being told that our u and v are coming from R4. They are subspaces of R4. So the solution set will also be a subspace of R4. Okay, so that means in that space there, you just fill in that your k is equal to 4. Now the matrix A, I'm reading further now. The matrix A, which should be a row matrix or a row vector, has only one pivot, and that one pivot, that is the first non-zero entry in the row. Yes, thus A has 3 free variables. Yes, look at it here. The pivot is the first non-zero element, and the first, where is it? A will have a row, this thing, okay, and then it says the first non-zero entry in that row, okay, and the first non-zero entry is 7. So the number of free variables will be 2, okay. So thus, so there's something they said there, thus, I'm just reading for you the whole thing and then highlighting where there is a question. So it says, thus, A has dash free variables. Okay, so how many free variables does A have? Okay, and of course, you can see it even from this place that this will be the leading variable there, and so it will have 2 free variables, which will be x3 and x4. So 2 free variables, and then what again? Consequently, the dash vectors in the basis. Okay, so now it's now asking us consequently, okay, it's not going to be 2 free variables. Watch. You know why it's not going to be 2 free variables? Because there is also x1 in the set of variables. Look at it here. That even though the x1 is of 0 coefficient, the only thing is that, and there was a point where we did that example where x2 was having a coefficient of 0. So, but we now counted it as a free variable since it was in row 2. So because there was no x2, so it became a free variable. So that means your x1 here is also a variable, and of course you can see it here. So since 7 is the leading coefficient, so every other variable there will be a free variable. So x1 is a free variable, x3 is a free variable, and x4. Okay, so here should be 3. Sorry about that. And you know that it is the number of free variables that produces the dimension of a particular subspace or a space. Okay, so then that helps us to fill the next question there. So it says consequently there are, even though they did not put R there, so there are dash vectors in the basis set. So there are dash vectors in the basis set. And what is that? So there are 3 vectors. Remember, like I said, it is the free variables that determines the number of vectors you will have in the basis, and that in the basis, and that automatically determines the dimension. And I think that's the last thing they wrote here. Therefore, the dimension of u, which is written as the mu, is equal to 3. All right, and so they left that space there. The dimension of u is equal to 3. All right, so you have been able to answer the dimension of u as 3, and okay, and so the next now is to go for the other ones, all right, which they also did with us in page 30, following some steps as well. So let's go up. Okay, so the next thing we have there is that, and they have said, suppose that your u, okay, so they now gave, assuming that your u now, which we said is produced by 3 vectors. Suppose that those 3 vectors are v1, v2, and v3. It says then present a set of v1, v2, v3 to show that you understand how they look. Okay, of course, it's very easy to see. So see how it's going to be. Remember that Okay, so remember that our u, let me come up here. So remember that our u is this set here, where you have this one, all right, that generated this particular matrix. Okay, so what that means is that from here we can try to solve that equation, or sorry, that matrix. Okay, and to solve it, of course, I can make use of this. To solve it, what you have, just permit me to show you what I mean. Let me bring back the matrix, the equation. So I had 7x2, or let me even put 0x1 into it, plus 7x2, or no need, that would be not necessary, then plus x3 plus x4 equal to 0. So all we need to do is to make x2 the subject here, since it is the one carrying the leading coefficient. So this is going to give us that our 7x2 is equal to minus x3 minus x4. So, and then since x3, x4, x1 are going to be the free variables, but then x1 is a 0, so it's only x3 that we will fix here. So let's fix x3 and x4. So we are going to say, okay, let me go down first before. So this is going to be equal to minus 1 over 7, dividing through by 7, minus 1 over 7 x3, then minus 1 over 7 again x4. Okay, so in this case, let my x3 be equal to x3, since it's a free variable. So I'm going to fix it. I'm going to fix it to itself, and then the same thing will happen to x4. I'll fix x4 to itself. Okay, so watch what is going to happen there. You are now going to have that your solution set for you is going to be something of this nature. X1, x2, x3, x4 is going to be equal to my x1 is okay, meanwhile, understand that I can also fix my x1, sorry, since it's also a free variable, let's also fix it. So that's going to give me the solution as x1, and then my x2 does also not have a value. Okay, sorry, it's the x2 only that has a value, and that's minus 1 over 7 x3, sorry, x3 minus 1 over 7 x4, and then my x3 is fixed, my x4 is fixed. So this is my solution, and then all I need to do now is to break it into vectors. And in breaking it into vectors, what I'm going to have is okay, let's see now. We are going to have how many variables do we have here? That will tell the number of vectors we are going to get. We have 1, 2, 3. That's 3 free variables. So you are going to have the first vector will be for coefficient of x1. So the coefficient of x1, I should have split this into 3 first before factorizing, but we can do it straight up. The coefficient of x1 in the first line is 1, in the second line is 0, third line 0, fourth line 0. So this, so these ones now will multiply x1. Then plus, we go to the next one, coefficients of x3, right? The coefficient of x3 in the first row is 0, second row minus 1 over 7, third row 1, fourth row 0. You close there, multiply by x3. And then finally, for x4, I'm going to have plus, that's going to give me coefficient of x4 in the first row is 0, second row is minus 1 over 7, third row 0, fourth row 1, and that's multiplied by x4. So that has given me the three vectors v1. So this is my v1, this is my v2, and this is my v3. So those are the three vectors that will be in the null space U. So this is our null space U, okay, which is spanned by these three. So you can actually remove this because this is the span of this, okay. All right, so but these are the three vectors they said we should find. This is our v1, v2, v3. So all you would do is because of your space, you can just write from here then to this place, and then you can identify this as v1, v2, and v3. Maybe on top or below here, you can do that depending on the space that you have. Okay, so now going forward, we are now told follow our procedure in I above. Where is the I above? Okay, if we go, have you seen? Okay, in I above, all right, we can have what exactly? Okay, this one now I think is for v. Okay, I think this is talking about v. That's the I now. Okay, so this we are now doing the second one. That's to get for the dimension of v. Of course, we'll follow the same process we followed for the dimension of u. Okay, so let's go there. So for I, it's just that it was not properly numbered. So we follow the same. So they said we should follow the same process. Follow the procedure in I above. In I above. Okay, that's what we want to do. And of course, if you do that, then what that means is just as we were able to write ax equal to 0 in I, we are going to also do the same here. So we are going to write ax, we will put v in the form of ax equal to 0. So and what is our v? Please, I will need that v again. Let me write it out here. Remember that our v is the set of x1, I'm trying to bring it from the material, x1, x2, x3, x4, such that x1 plus x2 is equal to 0, and x3 is equal to 5x4. This was what was given, but permits me to turn in this 5x4 to the other side and equate everything to 0 so that we can generate the null space, and so if it comes over, it becomes minus. Okay, so this is okay. All right. So with that, we can now generate the null space. So that is, we want to get ax equal to 0 again now. So in this case, we have two matrices, so that is going to form our A. So here we have 1, that's the coefficient of 1 here, of x1 is 1, and then x2 will be 1 also. Okay, so we have, and then that means, remember that this is from a space of where you have x1, x2, x3, x4. So that means the coefficient of x3 is 0 and the coefficient of x4 is 0. So that will be that for our A. That's from equation 1. And then onto equation 2, there is no x1, that's 0. There's no x2, 0 also. x3 is 1 and x4 is minus 5. Okay, and that is equal to, okay, no, let's not put equal to. So that's our A, and then our x is also going to be x1, x2, x3, x1 to x4. So let me put it this way, x1 up to x4 so that it won't take much of our space. That's our x. And then you can see from here that our v, which is the whole of this composure here, is going to have two free variables. So what are the free variables? You can see that this is a leading variable here, a leading coefficient, and there's another leading coefficient here. So in row 1, the leading coefficient or the leading variable is x1, and in row 2, the leading or pivot, now the pivot variable is x3. So that means there are two x values that are going to be free variables, and those x values, so I can write that. So this implies that our free variables are x2 and x4. Okay, so that means we have two free variables, and if we have two free variables, what it automatically means is that the dimension of v is equal to 2, and that's what the second question asked us to do. Now, but remember that they also asked us to get the basis, and to get the basis we will need to now get the vectors. We need to get the vectors. All right. Meanwhile, I hope you are aware that these three vectors that we got here, these v1, v2, v3, are the basis for null space U. All right. Of course, we wrote it here. Null space U is equal to, where is it? Yeah, is the span of our null space U is spanned by v1, v2, v3. So v1, v2, v3 that we got here are actually the basis for your U. Okay, so let's go. So now to get the basis for V, all we need to do now is that we will try to also get the solution set for that particular this thing. And how do you get the solution set? So we just start. So we can say to get the basis for V, or null space V, or we can just leave it that way. We start from that row 2, which is x3 minus 5x4 is equal to 0. So if we solve this, you will get that x3 is equal to, although it was even given to us already, x3 is equal to 5x4. And then if we solve the first equation that was given to us, we will also get the value for x1. Remember that x1 and x2 are the only pivot variables. So and that first equation is x1 plus x2 is equal to 0. So which will give that x1 alone is equal to minus x2. So with these two values, then we can produce our complete set of solution, which is x1, x2, x3, and then x4 is going to be equal to, now here your x1 is equal to minus x2. Let me use this one. And our x2 is a free variable, so you will fix it. So you fix it to itself. x3 is equal to 5x4. And then x4 is a free variable. You will also fix it. Okay, so from here, we can now split it into the two vectors. Now, it's going to be two vectors because you have two free variables. And if you check here, you only have two vectors. That's two variables here. So I'm going to bring out coefficients of x2 first. In the first row is minus 1, second row is 1, third row 0, 0. Multiply by x2 plus, permit me to write x4 here. So our x4 is going to be, coefficient here is 0, coefficient here is 0, then here is 5 and 1. and then that is multiplied by x4. So the basis, the null space of V, that means the basis is, it is spanned by the vectors, two vectors v1 and v2, but I'm going to be writing the vectors here, -1 1 0 0, and then 0 0 5 and 1. So the basis for V are just these two vectors, and that's why, like we said, the dimension is equal to 2. And that completes the question of II. So we go over to the third one, which is talking about U intersection V. And then there they decided to lead us again. You can see in II, they allowed us to do it ourselves, but in then III, they decided to lead us again. And then they said that U intersection V are the vectors. Let me bring out the points given here. Are the vectors x1, x2, x3, and x4, okay, that satisfies the conditions in U and V. You know intersection now, so that means it's going to make up all the equations you have in U and V. So that includes 7x2 plus x3 plus x4 equal to 0. This is the one in U, while the one in V was x1 plus x2 equal to 0, and then the last one was x3 equal to 5x4, which I brought to the other side, and then he gave me x3 minus 5x4 equal to 0, because we want it to be giving us 0 on the right, so that it will be in a null space form. Okay, so from here you will then generate your ax, that means your a and your x. Of course already you know your x, that your x is going to be equal to x1 to x4. Okay, so let's go. So here our x1 for the first equation is 0, x2 is 7, x3 is 1 1. You know what we got before now, 1 1, and then here is 1 1 0 0. Here it is 0 0 1 minus 5. Okay, so this is our a, and our x is x1 up to x4. Okay, you can put that if you want, and then you know it's equal to 0. So this is our a and this is our x. Now, having brought out all this, now the reason we are bringing out all this is so that we'll be able to determine the free variable, so that once we are able to determine the free variable, that will tell us the dimension of this particular U intersection V. And of course you can see x1 is okay. In the first row, x1 is a free variable, but then you may need to interchange some rows so that you will be able to see it clearly, because you know that in Gaussian elimination we are allowed to interchange rows. So my a is the same thing as 1 1 0 0, then I can make row 1 to become row 2, so that's 0 7 1 1, and then I'll have 0 0 1 minus 5. Wow, this is beautiful. It gave us a perfect echelon form. Okay, so it gave us a perfect echelon form reduction, and then you can clearly see that x1 is represented as a pivot, x2 is represented as a pivot, and x3 is represented as a pivot. So only free variable here is equal to x4. So we have only one free variable. Therefore, the dimension of U intersection V is equal to 1. So the dimension is equal to 1, and that's what they asked us to get. And then to get the basis all you need to do is to now solve what you have here, and if you solve, you discover that all of them will only depend on x4, because x4 will be the only free variable. So starting from equation 3 here, that's row 3, we have 1. That one now is x3 minus 5x4 is equal to 0, which will give you that x3 is equal to 5x4. Now go to equation 2. You will get that 7x2 plus what do you have there? x3 plus x4 is equal to 0. So which is going to give us, I think we have done that before also, it's going to give us x2 as equal to minus 1 over 7x3, then minus 1 over 7x4. But then we already have x3, and x3 is 5x4. So that means this is going to be minus 5 over, I'm multiplying now, minus 5 over 7x4. So I replace this with 5x4, and that gave me minus 5 over 7. I only need to get x2 in terms of x4. Alright, I'm back here. The first equation is x1 plus x2 equal to 0. So that means x1 alone is equal to minus x2. But you know x2 is already in terms of x4. X2. That means our x1, everything should be in terms of x4. And so our x1 will now be equal to, if you take the minus of this, you will get 5 over 7 x4. Because why are we doing that? Because x4 is the only free variable here. So we should write everything in terms of x4. So we should write everything in terms of x4. Okay. Meanwhile, okay, look at what we did here. Sorry. Oh my goodness. We didn't add what we've got here. Let me bring back that thing that I removed. Okay, see now. You know, I only replaced this one, and then I forgot to bring down minus 1 over 7x4. Sorry about that. So this was supposed to be, if you add these two things, you are supposed to get, of course, minus, you are just adding minus 5 over 7 and minus 1 over 7, which is equal to minus 6 over 7. Sorry about that. So you have minus 6 over 7 x4. So which means that this one also will change. So our x1 will become plus now. So plus 6 over 7 x4. And immediately, you don't even need to form that our long solution set. But if you want, you can form it. But you can immediately bring out the basis. So the basis of U intersection V is going to be the set that will contain only one vector. And the vector is going to be x1. Just pick out the coefficients of x1, x2, x3, and all that. So the coefficient of x4 in x1 is 6 over 4 only. Sorry, 6 over 7, comma, the coefficient x2 is equal to, where is it? This one. So the coefficient of x4 there is minus 6 over 7. And then x3, where is x3? Okay, x3 is equal to 5x4. And the coefficient there is 5. And then x4 is fixed to itself. So you can just say x4 is equal to x4. And the coefficient there is 1. Okay? And that gives you the only vector that will be in the basis of U intersection V. But like I said, you know, you can form that complete solution set that I used to form. So that you will be learning it. You know, when I used to do x1, x2, x3, x4 here. Okay, so you know what is that? That is going to be, you bring in your x1. X1 is 6 over 7 x4. X2 is minus 6 over 7 x4. X3 is 5 x4. And x4 is x4. So this is where I got this. So if you now bring out x4 here, so everything will just be the coefficient, and that's going to give you this. And so you have only one vector as the basis for this. So I have only this, this and this, and then all multiplying x4. So, and that's because x4 is the only free variable you have in this particular in this particular set that, or vector space that we are given, which is our U intersection V. Okay, and so that concludes the number one question of module 4. Okay, so module 4, sorry I didn't describe module 4. Module 4 has 3 questions, and there are, is it 3 now? Let me be sure. Yeah, 3 questions, and we just concluded the first one. Okay, so what do we do? Okay, let me see. Okay, so I think this is the end of this page. Okay, so we go to a new page, and then we will see whether we will continue or we should okay, should we continue with the second question? Let me see how big it is. It's really big. 9, up to 9 questions there. This is heavy. Okay, I'll probably end this video here. Okay, so we will do the other part of module 4 in the next video. Okay, so permit me to end at this point. So we'll see, that means for question 2 and 3 we will see that in another section, and that will be the end of module 4, and we will finally get to the last module, which is module 5. All right, see you in the next one. Please kindly subscribe, please kindly make comments, and then let us know if you have any other question. Okay, bye.